So the first factoring technique we want to gain practice with is the technique of bringing out the greatest common factor of a polynomial. So the first thing we need to know how to do is how to determine the greatest common factor among a set of monomial terms. So in this example, we have two monomials, 16y to the fourth times u to the sixth times v squared, and 24u to the eighth times v to the seventh. Those are both monomials because they don't have any addition or subtraction going on inside of them. They're built only out of a product of powers of various variables. And the question is, what do those two expressions most have in common? What can they both agree upon as far as the pieces that they are built out of in a multiplicative sense? So what's our strategy going to be to find an answer to that question? What we want again is, what is the most that these two expressions can share in common multiplicatively? To find it, we're going to go piece by piece. We're going to take each expression here and factor it completely. Figure out what are the pieces, the building blocks, the multiplicative building blocks that make each of these expressions have the value that they have. And we're going to factor them using a technique that you may recognize from the factorization of integers. We're going to use a factor tree. But we're going to include the variables in here as though the variables were also like prime factors. So we're going to split apart that y to the fourth by seeing it as a product of 4 factors of y and so forth. Once we've completely factored each of the expressions, we're going to match up as many common factors from the first expression as from the second expression, as many of them as we can find. Once we've done that, then multiplying those common factors together will give us the so-called greatest common factor, as long as we've gotten a maximal number of them. We're going to do this kind of a really long roundabout way the first time, and then at the end we're going to make an observation that can hopefully save us a little bit of time the second time around. But hopefully this explanation will help you to see why the shortcut that we're going to see actually works the way that it works. So let's get our factor trees cooking. Our first expression, 16y to the fourth u to the sixth v squared, we're going to start by separating the constant factor, the 16, from the variable factors, and separating the variable factors with different bases from one another. So I've got a 16, a y to the fourth, a u to the sixth, and v squared. Likewise with the second expression. And then for each of those factors that's at the end of these branches right now, we'll factor it. 16 is 2 times 8, and 8 is 2 times 4, and 4 is 2 times 2. So there is a complete factorization of the number 16. That's where all the arithmetic is going to happen in this problem. Meanwhile, the y to the fourth can be seen as y times y cubed, and y cubed can be seen as y times y squared, and y squared can be seen as y times y. So that's a really sort of overbearing way to say that what we're really doing here is we're trying to take those 4 powers of y and split them all apart so that we can see that we have a total of 4 factors of y that make up that part of this expression. Likewise with the v squared, likewise with the u to the sixth. So I'm running out of room a little bit here, but you can imagine that in this factor tree, we would get at the ends of the branches where all the prime factors reside, a total of 4 powers of 2, a total of 4 powers of y, a total of 6 powers of u, and a total of 2 powers of v. So the prime factorization of our first expression here can be written out in complete gruesome detail, the way that you see it here. So now we're seeing every single multiplicative building block that makes up 16y to the fourth, u to the sixth, v squared. And we can't break that apart any further. If we do the same process to the second expression, we'll factor 24 as 2 times 12. 12 is 2 times 6. 6 is 2 times 3. And since 2 and 3 are both prime, we can't factor that any further. Likewise, the u to the eighth and the v to the seventh, we can split those apart into their constituent u's and v's. So if we write out the prime factorization of our second expression in all of its gory detail, we'll get 2 times 2 times 2 times 3 times then 8 factors of u times 7 factors of v. Cool, so now we know what makes each of these expressions have the value that it has. And now it's a matter of matching up as many common factors as possible. So I want to be looking for pairs of, let's say, purple 2's that match up with brown 2's in this example. So there's one pair. And because these two expressions share a 2 in common, that means that their greatest common factor will have that 2 as one of its factors. But then there's also a second and a third factor of 2 that they both share. But that fourth 2 that our first expression has is not shared by the second expression. So that purple 2 does not have another brown 2 to match up with it. So we won't include that 2 in our prime factorization. So in other words, our greatest common factor is going to have a total of 3 powers of 2 in its factorization. All right, that 3 that the second expression has also doesn't match with anything in the purple expression here, so that 3 goes away. And we now know that the coefficient, the numerical factor in our greatest common factor, is just going to be 2 times 2 times 2, or 8. Now let's start matching up the variables. Well, there are no y's whatsoever in the second expression. So all of those y's that are a part of our first one are not going to have matches. So they're going to go away. They're not a part of our greatest common factor because they're not common to both. Meanwhile, there are actually u's in both the first and second expression. How many of them? Well, we can match up a total of 6. Right? There are 6 purple u's and actually more than 6 brown u's. And so if we match them up by pairs, we're going to get a total of 6 powers of u that match up in both of our expressions. Now, the second expression, the one on the right, actually has a couple of surplus u's that don't have matches, so we won't use those. Likewise with the v's. We have 2 purple v's and actually a whole bunch, 7 brown v's. So if we're matching them up, we can match up a total of 2 pairs of v's that are in both sets of expressions. So the greatest common factor is going to have those 2 factors of v, and then all the surplus v's that reside in the second expression are going to just go away. So we found now as many matches as possible between the factors of these 2 expressions, and so it's just now a matter of simplifying what we have. 2 times 2 times 2 is going to give you 8. Multiply those 6 factors of u together to get u to the 6th. Multiply those 2 factors of v together to give you v squared, and the greatest common factor of these 2 expressions is 8 u to the 6th v squared. All right, well, that was a lot of work for something that when later on we have to use this technique inside of a more complicated technique to factor polynomials, we would like to be able to do this with a little bit fewer steps. So now that we've seen why this process works, let's look at a way of getting to this end goal that's a little bit quicker. And here's the observation that we can make. The observation is that the number of factors of u and v that we ended up with in the end were actually numbers that belonged in our original problem. Notice u to the 6th and v squared were both part of our original expressions. So how do we know what powers of our variables we need to use? Well, where did this u to the 6th came from? It came from a comparison between the u to the 6th that was a part of our first factor and the u to the 8th that was a part of our second expression. And we chose that factor that has fewer powers of u. Likewise, v squared versus v to the 7th from the first expression and the second expression. We chose the factor that had fewer powers of v. After all, we're trying to match them up. And that expression which has fewer powers of a given variable or a given prime is going to be the one that limits how many we get in the greatest common factor. So what's the shortcut? The shortcut is to take the least exponent on every prime factor or every variable factor. So we ask, for example, we would ask ourselves the question, how many u's belong in our final answer? Well, our first expression had 6, our second expression had 8. So between those 2, we're going to choose the lesser. So our greatest common factor will have 6 factors of u. Likewise with the v's. Our first expression had 2 of them, second expression had 7 of them. So we should choose the lesser and have v to the 2. So to find the greatest common factor of 2 monomials, we're still stuck with doing the factor tree process probably to find the greatest common factor of the numerical coefficients. So to find the greatest common factor of 16 and 24, to know that that's 8, we probably do want to use a factor tree and match up the terms, the common factors in 16 and 24 to find that 8 is the greatest common factor of those 2. But once we've decided on the numerical coefficient of the GCF, the greatest common factor, then to figure out what the variable parts should be, the variable factors should be, just take the lesser exponent on each prime or on each variable. So the lesser exponent on the u's will give us u to the 6th. The lesser exponent on the v's will give us v squared. And then notice also that we don't have any y's in our final answer. And the reason we don't have any y's in our final answer is that we could see it as a comparison between the 4 factors of y that are in our first expression and the no factors of y that are in our second expression. Choosing, therefore, the lesser of the 2 exponents makes us choose to have no factors of y in our final answer.